Flick a switch and the lamp lights at once. So the electrons must race down the wire near the speed of light, right? They do not. The electrons drift along slower than a snail, often less than a millimeter every second. That is the puzzle this topic quietly solves. To explain it, we need three ideas working together: charge that comes in fixed lumps, current that measures how fast those lumps flow, and a single equation that ties the flow to the speed of the electrons themselves. Master these, and every electricity question opens up. Electric charge, symbol Q, is measured in coulombs. But charge is not a smooth fluid you can pour in any amount. It is carried by particles, and the smallest lump is the charge on one proton. The elementary charge, E, equal to 1.6 times 10 to the minus 19 coulombs. Because you cannot have half an electron, any charge must be a whole number of these lumps. That is what we mean by charge being quantized. Q equals n times E, where n is a plain counting number. The Mach scheme wants those exact words. Charge exists only in integer multiples of E. Here is the test that catches people out. Suppose an oil drop is measured at 2.4 times 10 to the minus 19 coulombs. Divide by E and you get 1.5. Not a whole number, so that charge simply cannot exist. Quantization is a hard rule, not a suggestion. Now set those lumps moving. Electric current, symbol I, is the rate of flow of charge. That word rate is doing all the work. It means divided by time. Right current is the flow of charge and you score 0. It is charge per second, I equals Q over T. Rearranged, charge equals current times time, and that defines the coulomb itself. 1 coulomb is the charge passing when 1 ampere flows for 1 second. So a current of 45 milliamps for 3 minutes delivers Q equals 0.045 times 180, which is 8.1 coulombs. And once you know the charge, the lumps from earlier come back. 8.1 coulombs divided by E is about 5 times 10 to the 19 electrons through that resistor. Two equations, Q equals IT then Q equals NE, chained together. Half of paper 2 electricity is exactly this move. Before the equation, one warning about direction. In a metal, the things that actually move are negative electrons, drifting from the negative terminal to the positive. But long before electrons were found, science had already agreed current runs from plus to minus. We never undid that. So the rule is simple. Every arrow, every symbol I, every left-hand rule later in the course uses conventional current, positive to negative. Only switch to electron flow when a question says the words electron flow. Get this wrong and a whole circuit answer flips backwards. Now the centerpiece. We want the link between the current and how fast the electrons actually crawl. Picture a wire of cross-section area A. In a time t, the carriers shuffle forward a distance v times t, sweeping out a little cylinder of charge. Build it up in 4 steps. The cylinder's volume is area times length of vt. Multiply by the number density n, the carriers packed per cubic meter to count the carriers. Multiply by the charge on each q to get the total charge. Then divide by time because current is rate of flow. The t cancels, and out drops the equation the syllabus wants you to derive. I equals nAvq. Current equals number density times area times drift velocity times the charge on each carrier. For electrons, Q is just E 4 quantities, one tidy line. One trap lives here. Little n is number density per meter cubed. Big N is the total count of electrons, just a number. If a question hands you n and a volume, you must divide to get n first. Check the units. If it ends in per meter cubed, it is the n you want. Charge cannot be created or destroyed, and that single fact gives us Kirchhoff's first law. At any junction, the total current flowing in equals the total current flowing out. Nothing piles up, nothing leaks away. The sum in equals the sum out every time. So if 5 amps enter a junction and 2 amps leave one way, the last wire must carry 3 amps out, balancing the books. And in a plain series loop with no junctions at all, the current is identical everywhere. Charge is never used up by a bulb, only energy is. Time for the real thing, a standard pape 2 question. A silver wire of diameter 1.2 millimeters carries a current of 3.5 amps. The number density in silver is 5.9 times 10 to the 28 per meter cubed. Find the mean drift velocity of the electrons. First, the trap that sinks half the candidates. The area. Diameter is 1.2 millimeters, so in meters that is 1.2 times 10 to the minus 3. Area is pi d squared over 4, And because we square a millimeter, the conversion brings a factor of 10 to the minus 6, never minus 3. Now rearrange the equation we derived. For I equals nAvE, the drift velocity v is I divided by nAe. Slot in the numbers, 3.5 over 5.9 times 10 to the 28 times the area times e. The denominator works out near 10,600. And the answer, about 3.3 times 10 to the minus 4 meters per second, quoted to two significant figures with its unit. That is a third of a millimeter each second, slower than the minute hand of a clock, yet your lamp still lit instantly. Puzzle solved. Here is the whole topic on a single page. Charge comes in lumps. Q equals NE, with N a whole number and E the elementary charge. Current is the rate of flow of that charge, I equals Q over T, which also defines the coulomb. Those two chain together to count electrons. The headline equation links flow to speed. I equals nAvq, derived by sweeping a cylinder of charge through the wire. And conservation of charge gives Kirchhoff's first law, the sum of currents in equals the sum out at every junction. And the traps that cost real marks. Always square the prefix when converting a millimeter area to meters squared. Never confuse little n, the density, with big N, the count, and keep the word rate in your definition of current. Nail those, and this topic is a guaranteed